Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 127, word ladder. Before we get into it, you guys know the drill. Subscribe if you haven't already, and if you have, drop a like, helps the channel grow. Alright, a transformation sequence from a word begin word to word end word using a dictionary word list is a sequence of words begin word goes to S1, S2, ... SK such that each adjacent pair of words differs by a single letter. For every s of I, for I less than or equal to 1, greater than or equal to 1, less than or equal to k, in word list, and note that begin word does not need to be in word list, and sk equals end word. So terrible explanation from Leetcode. Basically, given two words, begin word and end word, and a dictionary word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if such sequence doesn't exist. So basically ignore all this crap because Leetcode doesn't know how to write English. Anyway, so let's look at an example here. Let me get my pen back. So we have a begin word hit, and we have an end word cog, and this is our word list. And basically we have to start at hit and end at cog by changing one letter at a time. So what do we want to do here? Well, let's see. So from hit, what are our options we can change, right? Do we have anything that we could change the H from? It doesn't look like it because there's nothing with an I. So that means that we can't change that one. What if we change the T? Do we have HI? We don't. So that means we have to change the I, right? So let's see. We can go, can we get to an O, which is what we want in the middle anyway? So let's see if we can find, so if we go to hot, we can change the I into a O and we can get hot. So we'll have hit, we'll change it, and now we've changed it to hot. Now what we need to do is we need to continue going. So we want to start getting closer to our next word. So how can we change something here? So let's see. Well, what if we go... What can we do here? Well, we don't want to go back to... We can't use hot again. We don't want to use lot because that doesn't really help us because there's nothing we can go from the L's. We could... Why don't we go to dot? And from dot, we could change the T to go to G, which will give us the OG. And then from dog, we can go to cog. So it looks like we found a sequence here. So we'll go from hit, change this to an O, right? Then from hot, we're going to go to, dot. So we're going to change the H with the D. And then from dot, we're going to go to dog. So we're going to change the T to a G. And then from dog, we can change the D to a C and end up at cog, which is our final word. So we have found a solution. Okay, so it's pretty simple when you're just looking at the words and trying to figure it out on paper. Obviously, we have to write an algorithm, and just knowing how to do it on paper doesn't really help us because we have to code it up. So let's think about how we can actually solve this in a way that we can put into code. So we looked at an example, but obviously it's too easy to just do it on paper. We need to figure out how we can actually put it into code and solve this using an algorithm. So let's try to come up with an intuitive solution to this problem. And we'll use the principles that we used on the in-paper solution to kind of build out what our potential solution might look like. So we start with hit, right? And we know that we're only allowed to change one character at a time. So let's kind of write hit in three ways, right? So we could change the H, the I, or the T. So this could change to something with IT in it. It could be hit, and then this middle one could be anything. It could be H, I, and then this last one could change to any character we want. So what we want to do is basically, right, so we'll use a star here to represent that this can be any character. So what we want to do is, obviously we can build, this intermediate string by taking each character and kind of replacing it with this star. And what we want to do is we then want to match this to a list of words we can transform. So which one of these words in here has the same structure as this, where the first character can be anything, but the last two are it? So in this case, there's nothing here, so we can't really do anything there. What about this one, where we have H, O, and the middle character can be, the middle character can be anything, and the last character has to be T. So we see that hot matches this pattern. So from hit, we could get to hot if we change the middle character. And there's nothing else we could do there because that's the only one that starts with H and ends with T. What about H and I? Right? So H and I, well, let's see. We can't really do anything with that because there's nothing that starts with H and I. So this one's actually empty. So now we can try the same thing for the word hot, right? Hot. And again, there's 3 places we could place our little wildcard character, right? So it could be a star OT. It could be H a star T, which we already actually have. So we don't have to recompute that one. We can actually just use hot here. So we don't have to recompute it because we've already done that. And then we could change the T, right? So we could have HO and then star. So let's look at star OT. How many words in our word list match this pattern that also aren't hot, right? We don't want to have like a cycle here. So dot matches this pattern, right? Because the D can be anything, but then these 2 need to match. So we have dot here. Dot, let's see, lot matches. And that's about it. What about HO? What can we do here? We can't really do anything. There's no words that start there. So this is going to be an empty list. And this one we've already explored, so we don't need to do it again. And we can do the same thing for this word, right? So dot, how many words match this pattern dot? Apologies for the siren in the background. So with dot, so dot, again, we have 3 options. We can get rid of the star OT, which we've already done, actually. So we don't need to do it again. And then we can do what? We can get rid of, so we can do DO and then, D star T. We can do DO star. So obviously we've already computed this star OT, so we don't need to do it again. We're just going to ignore it. D with the middle, there's nothing that matches that pattern. So this is just an empty list. And here we get, DO, and we can basically, what's the only word? Dog, right? So now we are slowly creeping towards cog, because we know from dog, if we change the D, then we get cog, right? So essentially what we've done here is we've actually built a graph. And the graph, what it does is it maps every kind of like wildcard character to a list of words that we can go to, right? So this will be like, star IT as the key, and then a list of words here, right? Okay, actually that's a bad example because that one didn't have anything. So here we're gonna have, let's go clean this up. So we'll do star OT, and as we saw earlier, this has DOT and LOT, right? Lot. Oops, that's terribly written. So LOT. And as you can see, now we can continue our search from these characters, and then we just keep chaining. So really, this is like a breadth first search or depth first search through a graph. So all we have to do is actually build our graph by basically just, going through the word list and figuring out all the words we can reach from our current word if we just change one letter at a time. And then after that, we just need to start a BFS from hit, well, whatever the begin word is, and see if we can get to the end word by changing one character at a time, by basically traversing this graph. If we can, great, we return the number of steps it took. If we can't, then we just simply return 0, because that's, I guess, the base case. So that is how you solve it. Now, this problem is going to come down to 2 parts, right? Building the graph and then actually traversing it. Luckily, both are relatively simple, and you'll see that once we go to the code editor. But this is the general intuition of how we're actually going to build the graph, is by changing one character at a time in our, each word in word list. So basically, the star can be at the H, the star can be at the O, the star can be at the T, and then we're going to see which words would match that pattern in word list. That'll build the graph. Then, like I said, all we have to do is a breadth first search, because remember, we're looking for the shortest transformation sequence. So obviously, since we're looking for the shortest path in a graph, that should just scream breadth first search to you. Anyway, that's enough blabbing. Let's go to the code editor and type this up. It's really not that complex. It's about 30 lines of code, a lot of which is actually going to be some duplicated logic around actually changing these words and building each of the options. So again, enough talking. I'll see you in the code editor. We are back in the code editor. Let's write this up. Before we actually go forward and actually build the graph or do any of that stuff, we need to check a few edge conditions here, and that is that the begin word doesn't actually equal the end word. If it does, then we simply return 0 because there's no transformations we need to make. If we're not given a word list, obviously there's no way for us to get to the end word from the begin word because we don't have any words to use. And if the end word is actually not one of the words in word list, then we can't actually get there. So we need to check those 3 conditions before we can even start this problem. So these are going to be your base cases. So we're going to say if begin word actually equals to end word, or not word list. So basically if word list is an empty list, we can't do anything, or end word is not in word list, then we can't do anything there as well, right? Because we need to be able to reach begin word, end word from begin word, and if it's not in the word list, then obviously we can't get there. So we're going to simply return 0 in these cases as the problem tells us, right? I think right? If no sequence is possible, return 0. So close this out and give us more space. All right, so we know that we need to build a graph, right? Where the key to this graph is going to be one of our words, except for it's going to have a wildcard character. So if we have hot, right, that would be like star OT, or we could have H star T or HO star, right? So those are going to be your keys, and then the value is going to be a list of words we can reach, basically that match that pattern. So kind of like a regex matching, except we're not actually using regex here, just the wildcard character thing. So we're going to say graph equals to collections dot default dit. Jesus, I cannot type today. List. So that is going to be our graph. Now we need to actually build the graph. So we're going to go through all of the words in word list and basically add a wildcard to each position inside of it and check all of the words that could now be built from that. So we're going to say for word in word list, what we're going to do is we now need to go index by index and basically create all of those words. We're going to say, okay, for I in range len word, we're going to say that the new transformed word is going to be transform is equal to the word. So up until the ith index plus a star plus the rest of the word, right? So we're going to be replacing each character one by one. And again, if we think of our example with hot, obviously the first one, we would replace the H. So this would be star OT. Then, the next one is going to be this first index. So we replace that one. So H star T. And then the last index, we have HO star. So that's basically what we're doing here for each iteration, right? For the first iteration through this loop, we get this star OT. Then we get the star H star T and then HO star. So that's what we're doing there. And now that we have this transform word, we need to add that to our actual graph. So we're going to say graph. So if we have this transform word, then that means that, the append, we want to add our word to it. So basically we can reach that word if we have this current transform, right? Cool. So that is actually the building of the graph, relatively simple. Now we need to basically do our breadth first search. And remember that we're using a breadth first search here because, well, we have a graph and we're asked to find the shortest sequence between 2 points in a graph. That should scream BFS to you because breadth first search through an undirected graph will always give you the shortest path between 2 nodes. So let us now define our queue, which is going to store the breadth first search. So we're going to say collections.dec, and we're going to initialize this with a tuple. So begin word is where we're currently at and the number of steps we've taken, which is just going to be 1. Obviously, it has to be at least 1 because if it was 0, that means that begin word equals end word. So we have to start with 1. It is a little bit of a weird one in this question. I originally thought it would be 0, but I tried submitting it a bunch of times and I realized it has to be 1. So, okay, so that's the queue, and obviously we're doing a graph traversal, and we don't want to get caught in an infinite cycle here. As you saw when we went through the drawing, some words were repeated, and you can actually get caught in an infinite cycle, in which case we're never actually going to return anything, because we're just going to run recursively forever until the Leetcode times this out. So we're going to say visited, and this is just going to be an empty set, and this is what we're going to use to track where we've been. Okay, time to do the actual BFS now. So we're going to say while queue we're going to say that the word and the distance we've traveled so far is going to be q.popleft, pretty standard. Now what we need to do is we need to check whether or not we are at our destination. So we're going to say if our current word equals to the end word, then we just want to return our distance. Otherwise, we need to keep going. Now we want to add our word to the visited set because we just visited here. So we're going to say visited.addWord. And now what we need to do is we need to now check all of the possible things we can go from this word. So for example, if we have dog, right? All of the possible, new words we can reach, or whatever is in the graph for whatever star OG is, whatever D star G is, and DO star, right? Whatever the values of those keys are things that we need to add to our graph to continue exploring. So those are all the possible options we can go down at this point. So what we need to do is actually build out all of those possible words. So we're going to say for I in range, this is where we're basically going to repeat what we did up here. So for I in range len word, we're going to say transformed. And again, we're going to do word up until the ith index, and we're going to get that asterisk or star, and then plus word from the i+1 index to the end. So we're basically just building out that word again, so that way we can look up in the dictionary the values there. So what we're going to do now is actually get the words from our dictionary. So we're going to say if potential words, and I'm going to use the walrus operator here in Python. So basically what this does is if the statement evaluates the true, then it's basically going to, actually maybe this is not a good example because other languages don't have this. So we're going to say potential words equals to graph.get, so transform. So we want to get all of the possible words we can get by using transformed, and we're going to use none here. And the reason that I'm using graph.get instead of looking the key up directly is because we use the default dictionary. If you actually looked up this word, it would just initialize an empty list because it doesn't exist, right? This is kind of like one thing you have to watch out for when using default dict. If you didn't use a default dict, it's fine. You don't have to worry about this, but for us, we want to use graph.get, and then we actually want to check that we actually have some potential words. Otherwise, you're going to get into trouble here. So we're going to say if potential words. So as long as this list isn't empty, then we actually want to go through it and add it to our queue. If it's empty, then obviously we don't need to do anything here. So if potential words, so as long as we were able to get something out of the graph for that key, what we need to do is we need to say for potential word in potential words. What we need to do now is we just want to check we haven't actually been to that word before. Again, we don't want to get caught in a cycle, so we're going to say if potential word not in visited, I spelled visited wrong, visited, then what we want to do is just we want to add it to the queue for further processing. All right, so we're going to add potential word, and obviously this is now one more step in our BFS, so we're going to say distance +1. So that is your the BFS itself. So either we're going to return here because we found the end word, so we were able to reach the end word from the begin word using our BFS, or if we basically break out of this while loop for the BFS, that means that we were not able to reach it, and we simply return 0. I'm just going to run this real quick because I have a bad feeling I may have made a bug. Okay, cool, I didn't. There's just a lot of code. So, all right, so let's submit this, and let me clean this up, and it works. Okay, so what is the time and space complexity of our algorithm here? Well, let's go through this line by line. So, building the graph, what are we doing here? So, and actually one thing that we want to know is that if we look at the description here, each word is the same length, right? All the words, let's see. All the words have the same length here. So that's one thing to notice. So what do? We have for each word in our word list, so if there's n words in the word list, this is going to be big O of n. Then for every character in the word list, so if all the words have a length of m, we'll say m, so where m is length of word. So basically we're doing, so for every character in the word, we have to build this string here. And, you know, obviously we're concatenating strings, so this is going to depend on the length of the string that we're concatenating. So this is going to be big O of M. We're basically adding it to our graph, which is going to be a free operation because it's a dictionary key lookup. So we have, you know, 2 nested M's. So this portion here, building the actual graph, is going to take big O of M squared times big O of n. So for each word, we basically have to build all the possible transforms. So building the transforms is going to be big O of m squared. Remember, m is the length of the word, and n is the number of words in the word list. Okay, cool, easy. And then we obviously have the breadth first search here. So what are we doing? So for each iteration of our queue, obviously we're doing the exact same thing. So for every word in our current word, we have to build the transformation. So obviously each word, again, is going to be, you know, there's n words that we could potentially have in the queue. So times, so for each word, we need to go through each of the characters. So again, there's m characters in a word, times, again, we have to build this part. So that's going to be m. So, and then this is just like a free operation here because we're just doing lookups inside of a dictionary and a set. So the actual BFS part is also going to be, let's see, big O of m squared times n. So that means that our total time complexity is, again, it's just going to be big O of m squared times n because we can ignore the coefficients there. So we're going to say big O of m squared times n, right? That is going to be your time complexity. And the space complexity is going to be the same. Obviously, we have to basically store each of the possible transforms for each word. So remember that there's m squared possible transforms, and then we have n words. So the space complexity is also going to be big O of m squared times n. So that is your time and space complexity. That is how you solve word ladder. This question is pretty fun. This is like a pretty standard textbook question for actually learning breadth first search, and it's a pretty good question as well because it just tests your knowledge of can you build a graph and then traverse over it. So we see this come up a lot in Leetcode. Obviously, I wanted to do this question because there is a follow-up word ladder 2, which is literally basically the exact same thing, except for there's a little bit of a niche because in this case, we're not actually returning the number of steps. We're actually returning all the possible ways you can reach the end word because obviously we were just looking for the shortest path, but there could be a longer path, and word break 2 basically wants to know all the paths from begin word to end word, and we'll do that video shortly. So that is how you solve this question. If you enjoyed this video, please leave a like and a comment. It really helps me out with the YouTube algorithm. If you want to see more content like this, please drop a sub and let me know in the comment section below which questions you want me to solve. I'm happy to do them as long as they're not some stupid bullshit dynamic programming, because you guys should already know we don't do that crap on this channel. This is a dynamic programming free zone. We don't do that here. Anyway, thank you so much for watching and have a great rest of your day. Goodbye.